Welcome to this explainer. Today, we're diving straight into the fascinating, high-stakes world of the clinical chemistry lab. We're going to unpack the fundamental principles, the physical tools, and the absolutely crucial math that guarantees total accuracy and safety when testing patients' samples. Think of this as the literal anatomy of a perfect laboratory result. Let's get right into it.
Set the stakes for a moment by asking yourself this crucial question. What really separates a medical guess from a precise, life-saving diagnosis? Well, it isn't just advanced, flashy technology. It's flawless laboratory technique. It's the invisible discipline behind every single blood test, every metabolic panel, and every diagnostic marker out there. Seriously, if the foundational chemistry is flawed, the diagnosis is flawed. There's just no way around it.
All right, here's our agenda for today. 1. Universal language of measurement. 2. Reagents, purity, and water. 3. Understanding solutions and pH. 4. Essential laboratory supplies. And 5. The art of pipetting. Section 1. Universal language of measurement, the SI system.
Now, you might be wondering why we start here. Well, global standardization prevents incredibly dangerous misinterpretations of patient data. Using a universally accepted base unit, like moles per liter for a patient's analyte concentration, ensures that a doctor in Tokyo and a doctor in Toronto are speaking the exact same chemical language. Imagine if a clinical chemist in one country used mass and another used the amount of a substance. A totally routine metabolic panel could suddenly look like a critical emergency. The SI system is literally the bedrock that allows modern medicine to function across borders without those fatal communication breakdowns.
Section 2. Reagents, purity, and water. The lab's ingredients. Think of the clinical lab as a high-stakes kitchen. Here, the hierarchy of chemical purity is absolutely everything. We're talking about analytic reagent, also known as AR or ACS grade, or ultra-pure grade chemicals. Using these is critical because their impurity limits are strictly established by the American Chemical Society. On the flip side, commercial, technical grade chemicals, strictly forbidden. Their impurities just aren't controlled. And get this, even USP grade, which is heavily regulated to manufacture pharmaceuticals, isn't always pure enough for the complex, hypersensitive analytic procedures we do in a diagnostic lab. Crazy, right? And then we have the most common reagent of them all, water. Tap water is absolutely useless here. I mean, it's packed full of minerals and organics. Just as an example, the trace calcium found in everyday tap water could falsely trigger a critical hypercalcemia result on a patient's blood test. That could lead to disastrous medical interventions. So we absolutely must use heavily purified water, specifically designated as clinical laboratory reagent water. Labs go through intense methods to get this. We're talking distillation to boil and condense, deionization resins to strip out dissolved ions, reverse osmosis under massive pressure, and ultrafiltration to pull out microscopic particulates. This non-negotiable purity prevents invisible ionic interference from ruining our tests. Section 3. Understanding solutions and pH, the math. All right, let's talk about the math. In clinical chemistry, the patient's biologic fluid is the solvent, and the actual substances we're trying to measure are the solutes. So molarity, which measures the moles of solute per liter of solution, is our standard baseline for expressing concentration. But here's the catch. Because molarity relies on the total volume of the solution, it's highly subject to temperature fluctuations. A solution that's perfectly calibrated on a cool morning physically expands as the lab warms up during the day. This subtly but definitely alters that volume-based concentration. Now, contrast that with molality, because molality relies on the mass of the solvent. Using kilograms rather than liters, it's completely independent of temperature changes. In a really busy diagnostic lab where ambient temperatures can and totally do fluctuate, molality offers an unwavering standard. It is strictly a weight-per-weight measurement. That makes it the absolute preferred metric when you need extreme thermodynamic stability for a diagnostic assay. Next up, we have normality. This measures reactive capacity. When we're dealing with complex oxidation-reduction reactions or evaluating the exact combining power of acids and bases, normality is the metric that truly matters. It measures the number of gram-equivalent weights per liter of solution. So it goes way beyond just simple concentration to tell a chemist exactly how a solution is going to chemically behave and react the moment it hits a patient's sample. Okay, look at this. The Henderson-Hasselbalch equation mathematically proves the life-saving behavior of buffers. In a patient's bloodstream, a wild swing in pH is fatal. Human blood has a remarkably tight survival window.
And this elegant little equation shows us exactly how weak acids and their conjugate bases interact to maintain that razor-thin margin. It essentially proves the precise mechanism buffers use to absorb excess hydrogen or hydroxide ions, completely resisting massive pH changes that would otherwise denature proteins and destroy living cells.
Section 4. Essential laboratory supplies. The physical tools. Moving on to the physical tools. Almost all precision labware falls into a really strict functional binary. It's either to contain, marked TC, or to deliver, marked TD. A TC vessel holds exactly the volume stated, but when you pour it out, it leaves this tiny bit of liquid clinging to the walls. That means you didn't actually deliver the full amount. A TD vessel, however, is perfectly calibrated to dispense its specified volume, actively accounting for that leftover film. If you accidentally use a TC flask when a protocol clearly calls for a TD vessel, you'll subtly skew a patient's test results. It totally throws off all that delicate diagnostic math we were just talking about. And it's important to remember that vessel shape directly dictates its function. Class A volumetric flasks, with their long, thin necks, are specifically calibrated to hold one exact volume of liquid. We use those for incredibly precise diagnostic dilutions. On the other hand, Erlenmeyer flasks, with their wide conical bottoms and those straight-sided Griffin beakers, are designed for general holding and mixing. In those cases, pinpoint volumetric accuracy takes a backseat to easy access and stirring. Section 5. The art of pipetting. Precision in motion. Transferring exact volumes of these carefully crafted solutions requires immense skill. When you're drawing up or dispensing liquid, the pipette must be held strictly upright at a perfect 90-degree angle. No exceptions. Tilting the pipette changes the hydrostatic pressure and fluid dynamics inside the tube. This instantly throws off the exact volume calibration, totally ruining the delivery volume. Gravity literally must be perfectly aligned with the instrument to guarantee diagnostic precision. It really is a meticulous 4-step dance. Immerse, draw, wipe, and drain. Wiping the tip with a tissue, that is a non-negotiable step to prevent outside droplets from hijacking your volume. And the drain must be exact. The very bottom curve of the liquid, the meniscus, has to sit precisely on the calibration mark. Seriously, a microscopic failure at any of these steps, a forgotten wipe or an unaligned meniscus, fundamentally alters the chemical ratio and ultimately a patient's diagnosis. As we wrap up this explainer, I want to leave you with a final thought. How does the simplest lab tool hold the weights of a patient's health in the balance? We've seen today that clinical chemistry isn't just about pressing buttons on giant automated machines. It's an invisible discipline built on profound foundational blocks. From the global agreement on SI units to the absolute purity of diagnostic water, right down to the flawlessly vertical angle of a held pipette. Every single microscopic detail guarantees the life-saving diagnostic accuracy we all rely on. Thanks for joining me on this explainer. I really hope you never look at a simple drop of water in a lab the same way again.